We will continue this series of videos with Gaussian elimination and finding the solutions of a set of 3 equations with 3 variables. But a brief recap of the equation ax plus by plus cz is equal to some value k. This is the equation of a plane in 3D space. So we're looking at finding solutions in 3D where we have different planes like this, intersecting other planes. And this is where my 3D drawing skills fail, and there we might have a point as an intersection. But we don't always have a single point, as we saw with the 2x2 case. And I will quickly remove this because this might not actually help. But we're looking at planes in 3D space and intersecting them and looking at, are there any solutions in the intersection of the 3 planes? So we have as possible solutions. Well, if the planes intersect in a way that in the way that they're in a way where they're independent of each other, like we saw with the 2 equations, there can be one unique solution. There can also be infinitely many solutions. But there can be 2 flavors of infinitely many solutions. The solution set can be a line, or if all 3 equations are the same, the solution can be a plane. And there can also be no solutions. So no solutions. There can never be 2 solutions or 4 solutions. There's either one solution, infinitely many, or none. So, if we're looking at, so this will be an example where there's one single solution to, well, this, let me write out the system. X plus y equals 2, 5x plus 2y minus z is equal to 1, x plus 4 times y minus 2 times z is equal to 5. This is our set. Now, we've seen this one before. We know there is a single solution. And the single solution, if we end up at the end of our Gaussian elimination, will look like 1, 0, 0, 0, 1, 1, and this asterisk is some number. 0, 0, 1, and again some number. So if we have a single solution, we will end up with something like this. And then our solution can be read off these 3 values. Well, let's get started. A 3x3 example could be quite involved. I'm going to do this in more steps than absolutely necessary, just to make sure that we end up perfectly in this situation. Sometimes you don't have to go all the way to this situation. You can kind of use substitution to figure out the rest. And I think that's sometimes the approach of the book. But I will go all the way to this format. All right, here we go. So this is equal to the augmented matrix 3, 1, 0, 2, 5, 2, minus 1, 1, 1, 4, minus 2, 5. Now, to end up in this situation, I want a 1 in the top left corner. And what I can do is, now the order of these equations doesn't really matter. So I'm going to switch, I'm going to put this last equation on top. So this turns into, well, let's do this here. 1, 4, minus 2, 5. So that is that last equation. 5, 2, minus 1, 1, and 3, 1, 0, 2. So the only thing I've done is switch the first and the last rows. Now, I want to have zeros in these positions, so what I'm going to do is I'm going to subtract the first row 5 times from the second row, and I'm going to subtract the first row 3 times from the third row, which will give me, and of course this is one I've done earlier, 1, 4, minus 2, 5, 0, minus 18, 9, minus 24, 0, minus 11, 6, minus 13. Okay, and this is not very nice. So I could divide by minus 18, but, well, I see these are all multiples of 3. So I'm going to turn the second row into something else. So I have 1, 4, minus 2, 5. So this is the first row which remains unchanged. I can write this as, if I divide this row by minus 3, I get 0. 18 divided by minus 3 is 6. 9 divided by minus 3 is minus 3, and minus 24 divided by minus 3 is equal to 8. And the last row stays the same. All right, so I'm left with this. And ideally, somewhere, I'd get a 1. Now, I don't really want to divide this by 6 and then add it 11 times to the third row. Of course, this would work fine. But what I want to do as an intermediate step is, if I add the second row twice to the third row, this one, minus 11 plus 12, will equal 1. And these are some of the intermediate steps where you have to develop a bit of feeling, which you only really get by doing things many times. I will add the second row twice to the third. The first one doesn't change. Of course, the second row doesn't change either, because that's not the row I'm changing. I'm changing that third row. I'm adding this one twice to this one, and here I get my 1. Now, I then have to add this one twice to minus 6. So minus 6 plus 6 is equal to 0. And 8 times 2 is 16, plus 13 is equal to 3. And because I want this 1 not in the third row but in the second row, I simply flip these 2 around. 1, 4, minus 2, 5, 0, 1, 0, 3. Oh, that's good. I already have a 0 in that position, so that saves me another step. 0, 6, minus 3, 8. Now the next step, again, is to, I have 1 here, a 0, a 0. I have 1 here. The next step is to create a 0 here. So I subtract the second row 6 times from the third, and I will get a 0 there. The first row stays the same. 1, 4, minus 2, 5. The second row stays the same, 3. And so 6 minus 6 times 1 is 0. So that's this 0. Minus 3 minus 6 times 0 is still minus 3. And 8 minus 3 times 6 equals minus 10. Now you can already see the solution taking shape. This line here equals 0 times x plus 1 times y plus 0 times z is 3. So y is equal to 3, and 3z is equal to minus 3 times z is equal to minus 10. So we already know what the solutions for y and z are going to be. You could stop here and then substitute those values into this equation, but well, we might as well continue to this format completely. I'm going to divide the last row by minus 10. So I get 1, 4, minus 2, 5, 0, 1, 0, 3, 0, 0, 1, 1 over 10. Now the last step is to create a 0 here and a 0 there. That can be done by adding the last row twice to the first row, because then I'll get my 0 here, and I'll just use a different color, and that's you. And if I take the second row and I subtract that 4 times from the first, then I will get a 4 there. And we'll do that in one fell swoop, and we get the third row stays the same, 0, 0, 0, 1 over 10. The second row stays the same, 0, 1, 0, 3. And we find that 1, 0, 0, minus 1 over 3. So I've done 2 calculations in one go. Usually you would do this in 2 steps, but to calculate this value. But I've combined the 2 steps, and we are done. Is that really handy? No, let me do this in 2 steps. So I will first do the green operation to get that 0 there, and I'll have to continue there. So instead of doing it both at the same time, let's split it out, and because this is the way you would do it in an exercise anyway. So the last row stays the same, 0, 0, 1. That's not 1 over 10, that's 10 over 3. And I'm not going to write this as 3 1/3. That is a notation that is simply has no place in any academic setting, in my opinion. 10 over 3, because it's very annoying to have to calculate with, have to do calculations with fractions written in that way. Okay, so we add this third row twice to the first one. Well, of course, 1 plus 2 times 0 and 4 plus 2 times 0 still yield 1, 4. And I add 5. So here's my 0, 5 plus 20/3. And as 5 is 15/3 plus 20/3. So I'm going to rewrite this as a single fraction. I here get 35 over 3. All right, so we get the last step. We subtract the second row 4 times from the first row, and that yields the last one just stays the same, 10 over 3. The second row stays the same, is 3, and then I get 1, 0, 0, and then I get 35 over 3 minus, what is it? 4 minus 12, so that is 36 over 3, and that, well, 35 over 3 minus 36 over 3 is equal to 1 over 3. So I'm going to quickly erase this, and this is, so 3 times 4 is 12, we take that away, but I have written this in thirds. 12 is equal to 36 over 3, and this is minus 1 over 3. And we are in this frame, well, the end of our Gaussian elimination. We can write out x is equal to minus 1 over 3, y is equal to 3, and z is equal to 10 over 3. And this represents one single solution. It is one single vector, which represents one point in 3D space. So this is the situation where you have one single solution. And I know this seems like a lot of work, it's something you get handy in, but the main takeaway here is that if these calculations you can do, but you end up with a kind of a side picture where you can see that there is one single solution, because we have 1, 1, 1 and zeros everywhere else, and the solutions for x and y and z are given in these positions. So this is what it looks like if you have a single solution. The next part will be an example where we have infinitely many solutions and where we have no solutions at all.